What if everything you see, touch, and experience, every star in the sky, every breath you take, even the screen in front of you right now, wasn't quite as solid or real as it seems? What if, at the most fundamental level, reality is nothing more than an incredibly detailed illusion, a cosmic trick of light and information? This isn't the plot of a sci-fi movie. It's a genuine scientific possibility that's shaking the foundations of physics. Welcome to the holographic principle, one of the most radical and fascinating ideas in modern science. It suggests that our universe, with all its depth and complexity, might actually be a two-dimensional projection, like a hologram on a grand, unimaginable scale. And if that sounds impossible, hold on, because the evidence might just convince you otherwise. Think about the last time you watched a 3D movie. The images seem to leap off the screen, full of depth and life, but in reality they were just flat patterns of light. Now imagine that same concept applied to everything. The chair you're sitting on, the device in your hand, even your own body, all of it could be the result of information encoded on a distant, two-dimensional surface, like a cosmic movie screen we can't see. It's a theory that comes straight from the cutting edge of quantum physics and black hole research, where scientists have discovered something astonishing. The information inside a black hole might not be lost forever. Instead, it could be preserved on its surface like a cosmic hard drive. And if that's true for black holes, why not for our entire universe? This idea doesn't just challenge our everyday experience, it rewrites the rules of reality itself. For centuries, we've believed that space and time are the unchanging fabric of the cosmos. But quantum holography turns that assumption on its head, suggesting that space-time might emerge from something far stranger, a hidden layer of quantum data vibrating just beneath the surface of perception. Today, we're going to explore the mind-bending science behind this theory, from the experiments that hint at its truth to the profound questions it raises about existence, consciousness, and the nature of the cosmos. By the end of this journey, you might never look at the world the same way again. So let's dive in, because reality, as we know it, might be far more mysterious than we ever imagined. The holographic principle turns our understanding of reality inside out, literally. At its core, this mind-bending idea proposes that the three-dimensional world we perceive, with its towering mountains, swirling galaxies, and even the space between your fingertips, might actually be a projection from a two-dimensional surface, like a shadow cast by some deeper, hidden layer of the universe. It's as if everything we know is just the surface of something far more mysterious. And the strangest part, this isn't wild speculation. It's a theory born from the cold, hard math of black holes. When physicists like Jacob and Stephen Hawking studied black holes, they stumbled on a paradox. According to quantum mechanics, information can never truly be destroyed. But if a black hole sucks in matter, say an entire star, where does that information go? Hawking initially thought it vanished forever, evaporating into nothingness as the black hole radiated energy. But proposed something radical: the information isn't lost. Instead, it gets imprinted on the black hole's event horizon, the invisible boundary where nothing, not even light, can escape. Think of it like a cosmic fingerprint. Every detail of what fell in is preserved on the surface, encoded in tiny, sized pixels. Now here, where it gets even weirder. If a black hole can store all the information of a three-dimensional object on its two-dimensional surface, could the same be true for our universe? Imagine the cosmos as a colossal black hole, with every event, every particle, every ripple of gravity etched onto some distant, unseen boundary. This is the essence of the holographic principle, a universe where depth is an illusion, and reality is more like a movie screen projecting an unimaginably detailed image. But why would the universe work this way? One clue lies in the long-standing rift between quantum mechanics and theory of gravity. Quantum physics governs the tiny world of particles, where things can be in two places at once. Gravity shapes the cosmos, bending spacetime itself. The two theories refuse to fit together neatly, except perhaps in the holographic principle. By treating spacetime as emergent, a secondary effect of quantum information dancing on a lower dimensional surface, scientists might finally bridge the gap. Experiments are already hinting at this possibility. In labs around the world, physicists have created holographic simulations using ultra-cold atoms and lasers, observing how three-dimensional behaviors can emerge from two-dimensional systems. It's not proof, yet, but if the universe truly is a hologram, it would mean that every law of physics, every force we take for granted, is just the surface-level manifestation of a deeper, more fundamental reality. And that raises an even bigger question. If our world is a projection, what or who is doing the projecting? And T didn't just stumble upon the holographic principle, they fought for it. In the early 1990s, when most physicists were still grappling with the contradictions between quantum mechanics and gravity, these two visionaries saw something revolutionary hidden in the math of black holes. A towering figure in string theory, and T, a Nobel Prize-winning physicist, realized that the key to unifying these theories might lie in reimagining the very nature of space itself. Their breakthrough came from an unlikely place, the study of black hole entropy. In classical physics, entropy is a measure of disorder. Think of a messy room where everything's scattered. But black holes, those cosmic vacuum cleaners, seem to defy this logic. Jacob had already shown that a black hole's entropy isn't inside its crushing depths, but plastered across its event horizon, like graffiti on a cosmic wall. And T took this idea further. If a black hole's information, its entire memory of swallowed stars and planets, could be encoded on its two-dimensional surface, why stop there? Could the entire universe operate the same way? The implications were staggering. It meant that the three-dimensional world we experience, the textures, the distances, the very sense of depth, might be a kind of cosmic sleight of hand. Just as a hologram tricks your eyes into seeing 3D images from a flat surface, the universe could be projecting its richness from a hidden, lower dimensional layer. T likened it to a grand illusion, where spacetime itself emerges from quantum bits vibrating on some distant boundary, like ripples on a pond creating the illusion of depth. But not everyone was convinced. The physics community initially met their ideas with skepticism. After all, it's one thing to say a black hole stores information on its surface, it's another to claim everything does. Later recalled heated debates where colleagues dismissed the holographic principle as pure fantasy. Yet, as the math held up and new discoveries piled up, resistance turned to fascination. One of the most compelling validations came from string theory, and others found that in certain higher dimensional models, the equations describing gravity in 3 dimensions perfectly mirrored those of quantum particles dancing on a 2-dimensional surface. It was as if the universe had left a clue in its own blueprint. Look here. The secret is in the surface. Today, their once radical idea fuels cutting-edge research. From lab experiments simulating holographic universes to telescopes searching for anomalies in the cosmic microwave background, scientists are hunting for proof that we're living in a projected reality. And if T are right, it wouldn't just solve physics' biggest puzzles, it would redefine what it means to exist. After all, in a holographic universe, even the questions we ask might be part of the projection. Black holes aren't just cosmic anomalies, they're the ultimate puzzle boxes of the universe, forcing us to rethink the very fabric of reality. When Stephen Hawking revealed that black holes could slowly leak energy, now known as Hawking radiation, it sent shockwaves through physics. Here, why? If a black hole evaporates over time, vanishing into nothingness, what happens to all the information it swallowed? According to quantum mechanics, information, the precise details of every particle, every atom, can never truly disappear. But Hawking's calculations initially suggested it did, creating what became known as the information paradox. this wasn't just a minor inconsistency. It was a direct clash between quantum theory and general relativity, two pillars of modern physics that suddenly seemed irreconcilable. Enter the holographic principle. Instead of information being lost forever, physicists proposed something extraordinary. Everything a black hole consumes gets imprinted onto its event horizon, the point of no return. Picture this like a cosmic etch-a-sketch, where the details of entire stars and planets are scribbled onto a two-dimensional surface in unimaginably tiny pixels. This idea didn't just solve the paradox, it hinted at a deeper truth. If a black hole's three-dimensional contents could be perfectly described by data on its two-dimensional boundary, maybe the same logic applies to the universe itself. Think of it like a movie. What you see on screen is a flat image, yet your brain perceives depth, movement, even emotion. Now scale that up to reality. The galaxies, the planets, the very space between them. What if it's all a projection from some hidden underlying layer? This isn't just philosophical musing. The math behind black holes suggests that space-time might not be fundamental. Instead, it could emerge from quantum interactions happening at the universe's edges, like a 3D hologram generated from a 2D template. But how do we test such a mind-bending idea? Scientists are looking for clues in the fabric of space-time itself. Tiny fluctuations in the cosmic microwave background, the afterglow of the Big Bang, might carry imprints of this holographic encoding, like fingerprints left behind at a crime scene. Others are simulating holographic universes in labs, using ultra-cold atoms to mimic how three-dimensional behavior could arise from two-dimensional systems. While the evidence isn't definitive yet, each experiment brings us closer to answering a staggering question. If black holes obey holographic rules, could the universe be one grand, cosmic hologram? The implications are dizzying. It would mean that the solidity of your desk, the vastness of the night sky, even the flow of time, none of it is quite as it seems. Instead, reality might be the ultimate illusion, a shimmering projection from the edges of existence. And if that's true, it wouldn't just rewrite the laws of physics. It would redefine what it means to be real. String theory might sound like science fiction, tiny, vibrating strings replacing particles as the building blocks of reality, but it's one of the most serious attempts to solve the deepest mysteries of the universe. And here, where things get even more fascinating, this elegant framework doesn't just unify gravity with quantum mechanics. It also provides some of the strongest mathematical evidence for the holographic principle. At the heart of this connection lies something called the AdSCFT Correspondence, a discovery so profound it reshaped how physicists think about dimensions, gravity, and the very nature of existence. The AdSCFT Correspondence, proposed in 1997, revealed an astonishing duality. On one side, you have a higher dimensional universe described by string theory, a realm with gravity, black holes, and the familiar three dimensions of space we experience. On the other side, there's a lower dimensional quantum field theory, a flat, gravity-free world where particles interact on a two-dimensional surface. The mind-blowing insight. These two seemingly unrelated descriptions are mathematically equivalent. It's as if the richness of a 3D blockbuster movie could be perfectly recreated using nothing but the script, a flat, text-only version containing all the same information. This duality doesn't just hint at a holographic universe, it practically shouts it. If a higher dimensional space can be completely encoded on a lower dimensional boundary, then our 3D reality might be nothing more than a projection, an emergent phenomenon arising from quantum interactions happening at the universe's edges. Imagine a cosmic dance where every star, every atom, every ripple of gravity is just the shadow of something deeper, a hidden layer of quantum data vibrating on a distant, two-dimensional screen. String theory's role in this goes even further. The mathematics of this framework suggest that gravity itself might not be a fundamental force, but rather an illusion, a side effect of quantum entanglement between those lower dimensional bits of information. Think of it like a magician's trick. What we perceive as the force holding planets in orbit could just be the result of invisible threads connecting the universe's underlying code. Of course, this raises a tantalizing question. If string theory and the holographic principle are correct, could we ever find direct proof? Some physicists are looking for subtle anomalies in particle collisions or the cosmic microwave background, tiny glitches that might reveal the pixelated nature of reality. Others are simulating holographic systems in labs, using ultra-cold atoms to mimic how higher dimensional behaviors emerge from lower dimensional rules. While the evidence is conclusive yet, each discovery brings us closer to answering one of science's biggest mysteries. Are we living in a universe with depth, or is depth itself the grandest illusion of all? The implications are staggering. If string theory's holographic connection holds, it wouldn't just unite physics, it would redefine what we mean by real. Space, time, even the laws of nature might be secondary, emerging from a hidden quantum layer we're only beginning to understand. And that leaves us with a profound thought. If our 3D world is a projection, what does that say about the projector? Quantum entanglement is one of the most baffling phenomena in physics. A strange, invisible thread that ties particles together across unimaginable distances, defying our everyday intuition about how the universe should work. Imagine two coins flipped on opposite sides of the galaxy, yet somehow always landing on the same face instantly, no matter how far apart they are. That's the eerie reality of entanglement, where particles remain mysteriously linked, their fates intertwined even when separated by light years. But what if this bizarre connection isn't just a quirk of quantum mechanics? What if it's the very glue holding our reality together, the hidden scaffolding behind the holographic universe? This idea isn't as far-fetched as it sounds. In recent years, physicists have proposed a radical connection between entanglement and the fabric of spacetime itself. Their work builds on something called the ER equals EPR conjecture, a theory that merges two seemingly unrelated concepts: bridges, better known as wormholes, and the entangled particles described by and. The conjecture suggests that when particles become entangled, they might be connected by microscopic wormholes, tiny tunnels threading through the fabric of spacetime. It's as if the universe is stitching itself together with these quantum threads, weaving the illusion of depth and distance we perceive. Think of it like a tapestry. From the front, you see a rich, three-dimensional scene, a landscape with mountains, rivers, and sky. But flip it over, and you'll find it's just a tangled network of threads holding everything in place. In the holographic universe, spacetime could be that tapestry, with entanglement acting as the invisible threads creating the illusion of a continuous, solid reality. This would mean that the vast expanse between stars, the emptiness between atoms, even the passage of time, none of it is fundamental. Instead, it all emerges from a deeper layer of quantum connections, like ripples on the surface of a pond. Experiments are already probing this mind-bending possibility. In labs using quantum computers, researchers have simulated how entangled particles could generate spacetime-like structures, observing how simple quantum systems can mimic the behavior of gravity. Other studies suggest that the amount of entanglement in a system directly correlates with the geometry of spacetime it describes. More entanglement equals more space in the holographic projection. It's as if the universe is running a cosmic simulation, with entanglement as its code. But the implications go even deeper. If entanglement truly underpins spacetime, it could explain why the holographic principle works in the first place. Just as a 3D hologram emerges from interference patterns on a 2D surface, our three-dimensional reality might arise from entangled quantum data vibrating on some distant boundary. This would mean that every interaction, every collision of particles, every flicker of light is part of a vast, interconnected web, a universe where nothing is truly separate and distance is just another illusion. So where does that leave us? If entanglement is the hidden architecture of reality, it challenges not just our understanding of physics, but our very sense of place in the cosmos. We might not be isolated observers in a vast, empty space, but active participants in a universe that's far more intimate and interconnected than we ever imagined. And if that's true, the next time you look up at the night sky, remember, those distant stars might not be as far away as they seem. They could be linked to you and everything else, by threads of quantum entanglement, weaving the grand hologram we call home. If the universe really is a hologram, then the information it contains must be stored somewhere, like lines of code in a cosmic computer. And not just any computer, but something far more powerful, a quantum computer operating at the fundamental level of reality. This isn't just speculation. The way black holes preserve information, the very puzzle that gave birth to the holographic principle, bears an uncanny resemblance to how quantum computers process data. Both rely on systems where information isn't stored in traditional, localized bits, but instead is smeared across an entire network, interconnected in ways that defy classical logic. Take a quantum computer's qubits, for example. Unlike regular computer bits that are either 0 or 1, qubits exist in a superposition, both states at once, entangled with other qubits in the system. This allows quantum computers to perform calculations at mind-boggling speeds, solving problems that would take classical machines in mere seconds. Now, imagine scaling that up to cosmic proportions. If spacetime itself is built from quantum bits, as some theories suggest, then every particle, every force, even the vacuum of empty space could be part of a vast computational matrix, humming with information. This idea isn't just theoretical. The information paradox, the question of how black holes preserve the data of what they swallow, mirrors the challenge of retrieving information from a scrambled quantum system. In both cases, the data isn't lost. It's just encoded in a way that's deeply non-local, spread across the entire system like a puzzle with no single starting piece. Physicists like Seth have even proposed that the universe could literally be a quantum computer, with every interaction, every collision of particles, every flicker of light, representing a computation in this grand cosmic program. But what would that mean for us? If reality is computational, then the laws of physics might not be fundamental truths but emergent properties, like the rules of a video game emerging from its underlying code. Gravity, electromagnetism, even the passage of time could just be the universe's way of running its algorithms. Some researchers go further, suggesting that if we could hack this code, we might uncover hidden layers of reality or even find ways to manipulate spacetime itself. Of course, this raises as many questions as it answers. Who or what is running the program? Is there an ultimate source code to the universe? And if so, could we ever decode it? For now, these remain mysteries at the edge of science. But one thing is clear, whether as a hologram, a quantum computer, or something even stranger, the universe is far more than meets the eye. It might just be the most sophisticated information processing system in existence, and we're living inside it. Testing the holographic principle isn't just about thought experiments. It's about hunting for tangible, measurable glitches in the fabric of reality itself. One of the most ambitious efforts to catch the universe in the act is a high-precision laser interferometer designed to detect the faintest tremors in spacetime. Think of it like a cosmic microphone, listening for the static of a pixelated universe. If spacetime is truly holographic, it shouldn't be perfectly smooth. Instead, at the tiniest scales, it should fizz with quantum noise, like the graininess of an old photograph blown up too large. These lasers, bouncing back and forth over dozens of meters, are sensitive enough to pick up these hypothetical vibrations, evidence that reality might be built from discrete, information-rich pixels far smaller than an atom. But the isn't the only experiment probing these radical ideas. Over at the Large Hadron Collider, physicists are smashing particles together at nearly the speed of light, searching for anomalies in energy and momentum that could hint at extra dimensions or holographic encoding. Meanwhile, astrophysicists scour the cosmic microwave background, the afterglow of the Big Bang, for subtle irregularities that might reveal the universe's underlying code. It's like examining a painting for brushstrokes too fine for the naked eye, clues that what we see isn't the full picture. So far, the results are tantalizing but inconclusive. It hasn't yet detected definitive holographic noise, but it's pushed the limits of what we can measure, ruling out certain models of a pixelated universe. Other experiments, like those studying quantum gravity in lab-created black hole analogs, have found behaviors that eerily match holographic predictions. For instance, when researchers simulate black holes using ultra-cold atoms, they observe information spreading across boundaries in ways that mirror the holographic principle's math. It's as if the universe keeps dropping hints, whispering its secrets just beyond our reach. The challenge, of course, is scale. If spacetime's graininess exists, it's likely at the length, a distance so small that probing it directly would require particle accelerators the size of galaxies. Yet, even without smoking gun evidence, the holographic principle's explanatory power keeps it at the forefront of theoretical physics. It elegantly bridges quantum mechanics and gravity, two realms that otherwise refuse to cooperate. And if future experiments, perhaps with next-generation quantum sensors or space-based gravitational wave detectors, finally catch that elusive quantum fuzz, it would revolutionize not just physics, but our entire understanding of existence. After all, confirming the universe is a hologram wouldn't just answer old questions. It would force us to ask entirely new ones. This theory of relativity painted spacetime as a cosmic stage, a flexible, dynamic fabric that bends under the weight of stars and planets, dictating how matter moves and time flows. For over a century, this idea has been the bedrock of our understanding of the universe. But what if spacetime isn't the foundation at all? What if it's more like the screen of a movie theater, a surface where deeper, hidden processes play out? This is the radical possibility posed by the holographic principle, that spacetime might not be fundamental, but emergent, a secondary effect of quantum interactions we can't yet see. Imagine a river flowing smoothly over rocks. From a distance, the water seems like a single, continuous entity. But up close, you'd see it's made of countless molecules, each colliding and interacting in chaotic ways. Spacetime could be like that river, an illusion of smoothness created by trillions of quantum molecules buzzing beneath the surface. The holographic principle takes this even further, suggesting that the three dimensions we experience might be a kind of shadow, cast by quantum data stored on a two-dimensional boundary at the edge of the universe. It's as if the cosmos is a giant IMAX screen, and we're just the images projected onto it. This isn't just poetic speculation. The math behind black holes, where spacetime breaks down entirely, hints that fabric might be more like a tapestry woven from threads of quantum entanglement. When particles become entangled, their properties link instantaneously, defying the speed of light. Some physicists now believe these entangled connections could stitch spacetime itself into existence, like invisible threads holding reality together. If that's true, then the vast distances between galaxies, the curvature of gravity, even the flow of time, none of it is primary. Instead, it all emerges from a quantum network we're only beginning to map. The implications are staggering. If spacetime isn't fundamental, it could explain some of physics' biggest mysteries, like why gravity is so weak compared to other forces. Gravity might not be a force at all, but a side effect of spacetime's quantum origins, like the way the illusion of depth in a hologram arises from flat patterns of light. It could also rewrite our understanding of the Big Bang. Instead of an explosion in spacetime, the universe's birth might have been a quantum computation, a sudden boot-up of information that gave rise to the illusion of dimensions. But here's the real mind-bender. If spacetime is emergent, does that mean it can be manipulated? Could we one day reprogram the universe's underlying code to warp distances, slow time, or even create new dimensions? The answer might lie in the strange behavior of black holes, where spacetime twists into knots and information gets scrambled like a cosmic hard drive. If we can decode those processes, we might uncover the universe's ultimate cheat codes, keys to reality itself. For now, the question remains open. Is spacetime the canvas of the cosmos or just the painting? The holographic principle doesn't just challenge our assumptions. It invites us to see the universe as something far stranger, richer, and more mysterious than we ever imagined. And that's the beauty of it. The deeper we look, the less solid reality seems to be. Quantum mechanics and general relativity are like two brilliant scientists who speak entirely different languages. One governs the infinitesimally small, where particles pop in and out of existence and cats can be both dead and alive. The other describes the cosmos on its grandest scales, black holes bending spacetime, galaxies swirling in the void. Both theories work flawlessly in their own domains, but when they collide, the math explodes into nonsense. This isn't just an academic squabble. It's a crisis at the heart of physics, leaving us without a working theory for the universe's most extreme environments, like the singularity inside a black hole or the first moments after the Big Bang. Enter the holographic principle, a radical idea that doesn't just bridge these two worlds, it rewrites the rules entirely. Picture this: gravity, the force that sculpts the universe, might not be fundamental at all. Instead, it could emerge from something far stranger, a quantum dance happening on a distant, two-dimensional surface. Think of it like the way temperature emerges from the chaotic motion of molecules. You can't point to a single molecule and say, that's temperature. It's a collective effect. Similarly, gravity might be a side effect of quantum information interacting on the universe's edge, a cosmic illusion so convincing we've built entire theories around it. The math behind this is staggeringly elegant. In the late 1990s, physicists discovered that a higher dimensional universe with gravity could be perfectly described by a lower dimensional quantum system without gravity, a duality now known as the AdSCFT Correspondence. It's as if the universe came with a built-in translation manual, allowing physicists to swap between the languages of quantum mechanics and gravity effortlessly. Suddenly, problems that seemed impossible, like calculating what happens inside a black hole, became tractable when viewed through this holographic lens. But how could this possibly work in our universe? Imagine the entire cosmos as a giant quantum computer, where every particle, every force is just a computation happening on a two-dimensional surface. Gravity wouldn't be a force transmitted through spacetime, it would be spacetime itself, emerging from the way these quantum bits entangle and interact. This isn't just theoretical sleight of hand. Lab experiments with ultra-cold atoms have already shown how three-dimensional behaviors can arise from two-dimensional systems, mirroring the holographic principle in action. The implications are profound. If gravity is emergent, it could explain why it's so weak compared to other forces. In this framework, gravity isn't a fundamental pull but a statistical effect, like the way a crowd's movement emerges from individual steps. It might also solve the infamous information paradox of black holes, revealing how swallowed data isn't lost but smeared across their surfaces like cosmic graffiti. Yet the holographic principle isn't the only contender for quantum gravity. Competing theories like loop quantum gravity and string theory offer their own approaches, each with tantalizing clues. Some physicists argue that spacetime might be woven from discrete, pixel-like loops, while others see it as a vibrating string symphony. But what makes the holographic principle uniquely compelling is its audacity. It doesn't just tweak existing theories. It turns reality inside out, suggesting that the universe's deepest truths might be written on its edges, not in its depths. So where does this leave the quest for a theory of everything? If the holographic principle holds, the answer might not lie in unifying quantum mechanics and gravity as we know them, but in realizing they were never separate to begin with. They might just be different perspectives on the same underlying reality, one where dimensions dissolve, and the fabric of existence is woven from quantum threads we're only beginning to untangle. And that's the real magic of this idea. It doesn't just solve equations. It redefines what equations are even about. If the universe is a hologram, a vast, shimmering projection from some deeper layer of reality, then what role do we play in shaping it? This question takes us beyond physics and into the realm of consciousness itself, where the act of observation might not just record reality, but actively create it. At the heart of this idea lies one of quantum mechanics' most baffling quirks, the observer effect. In experiments like the famous double-slit test, particles behave differently when they're being watched. Without an observer, they act like waves, spreading out in all possible paths. But the moment someone or something measures them, they snap into a single definite state. It's as if reality remains fluid until consciousness steps in, collapsing infinite possibilities into one tangible outcome. Now apply that to a holographic universe. If our three-dimensional world is a projection from a two-dimensional surface, could consciousness be the mechanism that renders it into something solid? Some theorists, like physicist John Wheeler, proposed that the universe only takes concrete form when observed, a concept he called the participatory universe. In this view, we're not passive bystanders but co-creators, our perceptions weaving the cosmic hologram into focus. Imagine a video game that only loads the parts of the world you're actively looking at. The rest remains as unrendered code, existing only as potential. Could reality work the same way? This idea blurs the boundaries between science and philosophy in ways that make even seasoned physicists pause. If consciousness shapes reality, then the distinction between out there and in here starts to dissolve. The tree falling in the forest doesn't make a sound unless someone hears it, not because sound waves fail to propagate, but because the very act of hearing might be what crystallizes those waves into experience. Eastern philosophies have hinted at this suggesting that the material world is an illusion, or Maya, sustained by perception. Now, quantum holography offers a potential scientific framework for that ancient intuition. But here, where it gets thorny. If observation collapses reality, what counts as an observer? A human, a cat, a single-celled organism? Or does even the interaction between particles qualify? Some interpretations, like the Copenhagen School, argue that measurement, by any means, forces quantum systems to choose a state. Others, like the interpretation, go further, placing consciousness itself at the center of the process. Critics push back, pointing out that this veers dangerously close to solipsism, the idea that only one's mind is sure to exist. Yet, the math doesn't dismiss the possibility. In a holographic universe, where information is everything, the line between observer and observed might be thinner than we think. Experiments are probing these edges. Quantum eraser tests show that particles can seemingly retroactively change their behavior based on future observations, as if time itself bends to accommodate consciousness. Delayed choice experiments suggest that decisions made now can alter events that already happened. These aren't just party tricks, they're glimpses into a reality where past, present, and future might be woven together by observation. So where does that leave us? If consciousness is the loom weaving the hologram, then reality isn't just something we discover. It's something we participate in moment by moment. That doesn't mean we can manifest objects by sheer will. Physics still has rules. But it might mean that the universe is far more interactive, far more alive than we ever imagined. And if that's true, then every glance at the stars, every measurement in a lab, even your attention right now, might be part of the cosmic process that makes reality real. The idea that reality might not be what it seems isn't unique to the holographic principle. Another provocative theory, simulation hypothesis, suggests we could be living in an advanced computer program, like characters in a sophisticated video game. At first glance, these two ideas seem to echo each other. Both challenge the solidity of the world around us, proposing that what we perceive as reality is just the surface layer of something far stranger. But dig deeper, and the differences between them reveal just how wild the frontiers of physics and philosophy really are. Simulation theory, popularized by figures like Nick and Elon Musk, frames reality as a digital construct. Imagine an ultra-advanced civilization, perhaps our distant descendants, running ancestor simulations so detailed that the simulated beings inside them, like us, would have no idea they're not real. It's a concept straight out of sci-fi, but it's grounded in a chilling logical argument. If civilizations inevitably create simulations indistinguishable from reality, and if they run countless such simulations, the odds that we're in the base reality shrink to near zero. The evidence: glitches in the matrix, tiny anomalies in quantum behavior, or mathematical constants that seem suspiciously fine-tuned, like lines of code optimized for stability. The holographic principle, on the other hand, isn't about technology at all. It's a consequence of physics itself, emerging from the math of black holes and string theory. Here, the universe isn't a simulation running on some alien supercomputer. It's more like a cosmic projection, a three-dimensional illusion arising from quantum data encoded on a two-dimensional boundary. There's no programmer, no lines of code, just the fundamental laws of nature playing out in ways that make spacetime itself an emergent phenomenon. Yet despite their different origins, these theories share a startling implication. Reality might be an information-based construct. In simulation theory, information is processed digitally, bits and algorithms. In the holographic principle, it's quantum bits or qubits woven into the fabric of spacetime. Both suggest that the universe operates like a computational system, where the rules we take for granted, cause and effect, locality, even time, might just be the user interface hiding a deeper, more complex backend. So could these ideas be two sides of the same coin? Some physicists, like Seth, argue that the universe literally is a quantum computer with every interaction processing information. From this perspective, the holographic principle might describe the hardware, the way reality is built, while simulation theory speculates about the software. But there's a crucial distinction. The holographic principle is a scientific framework with testable predictions, while simulation theory remains, for now, a philosophical thought experiment. One is a map of reality's hidden wiring, the other is a story about who might be holding the wires. The real fascination lies in how both theories force us to confront the nature of existence. If reality is a hologram, it challenges our sense of dimensionality. If it's a simulation, it questions our very autonomy. Yet both ultimately lead to the same humbling thought: the universe is far weirder and far more wondrous than our everyday experience suggests. Whether we're projections or programs, the search for answers isn't just about physics, it's about rewriting what it means to be real. For thousands of years, spiritual traditions have whispered a startling secret: that the world we perceive isn't the full picture. In Hinduism, the concept of Maya teaches that reality is a divine illusion, a shimmering veil that obscures the ultimate truth. Buddhist philosophy speaks of emptiness not as nothingness, but as the absence of inherent, solid existence. The Tibetan Book of the Dead describes reality as a rainbow vivid yet intangible, appearing real but lacking substance. These aren't just poetic metaphors. They're ancient frameworks that eerily mirror what quantum physicists are now discovering, that the universe might be a projection, a cosmic sleight of hand. Take the Hindu parable of Indra's net, a vast web stretching across the cosmos with a jewel at every intersection. Each jewel reflects all the others perfectly, creating an infinite hall of mirrors where every part contains the whole. It's a striking parallel to the holographic principle's claim that every fragment of spacetime encodes information about the entire universe. Or consider the Buddhist teaching of dependent origination, which holds that nothing exists independently, everything arises in relation to everything else. Sound familiar? It's not far from quantum entanglement, where particles remain mysteriously linked across vast distances, as if the universe itself is a single, interconnected tapestry. These parallels raise a profound question. Were ancient mystics glimpsing the same truths that science is now uncovering, just through a different lens? Visionary physicist David thought so. He proposed that reality is an implicate order, a hidden dimension where everything is enfolded into a unified whole, only appearing separate when unfolded into our perceived world. His ideas drew direct inspiration from Eastern philosophy, suggesting that consciousness and reality might be deeply intertwined, another echo of spiritual teachings where mind and world are inseparable. Yet there's a crucial difference. Ancient wisdom often framed these insights as revelations to be experienced through meditation or enlightenment. Modern science demands evidence, equations, and experiments. The holographic principle isn't a metaphor, it's a mathematical framework with testable predictions. When physicists talk about information encoded on the universe's boundary, they're not speaking poetically. They're working with precise calculations that could one day be proven or disproven in a lab. This collision of worlds, mysticism and quantum physics, doesn't mean ancient sages had telescopes pointed at black holes. Rather, it hints at something even more fascinating, that deep truths about reality might be accessible through multiple paths, whether through inward contemplation or particle accelerators. The holographic principle doesn't validate spirituality, nor does spirituality prove the holographic principle. But their resonance suggests that when it comes to the nature of existence, humanity might have been circling the same staggering truth all along. So the next time you hear a physicist describe spacetime as an illusion or a monk speak of the world as a dream, remember, they might be standing on opposite sides of the same mountain, describing the same peak in different words. And that's the real magic, not that science and spirituality agree, but that they keep arriving at the same dizzying conclusions by utterly distinct roads. Mathematics doesn't just describe the universe. It might be the very fabric from which reality is woven. When physicists unravel the equations behind the holographic principle, they're not just solving abstract problems. They're deciphering cosmic blueprints, lines of code in the universe's operating system. Take entropy, the measure of disorder that Jacob first linked to black holes. His equation, simple yet profound, showed that a black hole's entropy isn't scattered through its crushing interior, but plastered across its two-dimensional event horizon. Each infinitesimal patch of that boundary holds exactly one bit of quantum information, like a pixel on a screen. The numbers revealed something astonishing. The maximum entropy any region of space can contain doesn't scale with its volume, as you'd expect, but with its surface area. It's as if the universe itself is hinting that what happens inside any space is fundamentally constrained by information written on its edges, a smoking gun for the holographic principle. The beauty of these equations lies in their universality. Just as E=² applies from the smallest atom to the largest galaxy, the holographic math works across scales. AdSCFT Correspondence, for instance, uses the elegant language of string theory to show how a higher dimensional space with gravity can be perfectly mirrored by a lower dimensional quantum system without gravity. The numbers don't just match, they sing in harmony, like two sides of a strip revealing they're actually one. This mathematical duality suggests something radical, that gravity, the force that shapes cosmic structures, might emerge from quantum entanglement, like a 3D shadow cast by 2D interactions. But the real magic happens when these equations collide with experiment. Consider the Ryu formula, which calculates how quantum entanglement entropy relates to geometry in holographic models. It predicts that the amount of entanglement between regions of space directly determines the area of surfaces separating them, as if the universe is stitching itself together with quantum threads. When researchers tested this in lab-made black hole analogs using ultra-cold atoms, they found eerie alignments between predicted and observed values. The math wasn't just describing reality, it seemed to be uncovering its hidden grammar. What's most striking is how these equations blur the line between physics and information theory. Claude Shannon's classic formula for information entropy, developed for telephone signals in the 1940s, shows up verbatim in black hole thermodynamics. Quantum error-correcting codes, designed to protect fragile qubits in computers, turn out to perfectly describe how spacetime itself might resist cosmic glitches. It's as if the universe runs on the same logic as our most advanced technologies, just operating at a scale we're only beginning to comprehend. The numbers whisper a tantalizing possibility, that beneath the complexity of the cosmos lies a simplicity so profound it redefines elegance. From the fractal patterns in galaxy clusters to the way quantum states entangle, mathematics keeps revealing a universe that's less like a machine and more like a symphony, where every note, every equation is part of a grander composition we're only starting to hear. And if the holographic principle holds, those equations might not just be describing the music. They might be the sheet music itself. Not every physicist is ready to embrace the idea that we're living in a cosmic hologram. For all its elegance, the holographic principle faces fierce pushback from scientists who argue it's more mathematical poetry than testable physics. One major criticism cuts straight to the heart of the scientific method. If we can't design experiments to confirm or disprove the theory, does it even belong in the realm of science? Critics point out that while the math behind holography is beautiful, its predictions often involve phenomena at the scale, trillions of times smaller than anything we can currently measure. It's like theorizing about invisible ink that only reveals itself under sunlight from another galaxy. Without concrete evidence, they argue, the principle risks becoming a modern-day epicycle, an elaborate explanation that's clever but ultimately untethered from reality. Then there's the problem of alternatives. Loop quantum gravity, for instance, offers another compelling approach to unifying quantum mechanics and relativity. Instead of reducing reality to a two-dimensional projection, this framework proposes that spacetime is woven from tiny, discrete loops, a fabric with genuine depth rather than an illusion. Supporters of loop theory highlight its ability to preserve locality, the notion that objects are directly influenced only by their immediate surroundings. The holographic principle, with its spooky non-local entanglement, seems to violate this at every turn. Why accept such radical ideas, skeptics ask, when other theories might solve the same puzzles without rewriting the rules of dimensionality? Even the holographic principle's greatest triumph, the AdSCFT Correspondence, has its detractors. The mathematical duality works flawlessly in hypothetical universes with negative curvature, but our cosmos appears to be flat or positively curved. It's like having a perfect key that doesn't fit the actual lock. Some physicists argue that until the principle can describe our universe's geometry without hand-waving approximations, it remains an intriguing thought experiment rather than a definitive theory. Others, like Nobel laureate Roger, go further, suggesting that holography's focus on information misses the deeper physical essence of reality. In his view, the universe isn't a data structure. It's a dynamic interplay of geometry and quantum state reduction. Proponents of holography aren't backing down, though. They counter that while direct evidence may be elusive now, the same was true for black holes and gravitational waves before technology caught up. The in-quantum simulator experiments are early steps toward testing these ideas, and future breakthroughs in quantum computing might finally crack the code. As for alternatives like loop quantum gravity, holography advocates argue they lack the same explanatory power for black hole information paradoxes, the very problems that birthed the holographic principle in the first place. And that AdSCFT mismatch. Researchers are already developing new models for flat and positively curved spaces, treating the original correspondence as a stone for more universal translations. The debate reveals something fundamental about how science progresses. Revolutionary ideas always face resistance, especially when they turn reality inside out. But whether the holographic principle ultimately prevails or gets supplanted by something stranger, one thing is certain. The questions it raises are forcing physics to grow in ways no one could have predicted. And that's how the best theories work, not by providing final answers, but by revealing how much we still have left to discover. Emergent spacetime isn't just a tweak to physics. It's a full-scale demolition of how we've understood reality for centuries. Think of it like this. We used to believe spacetime was the stage on which the universe's drama unfolded, an unchanging backdrop against which stars burned and galaxies spun. But if spacetime emerges from quantum interactions, then the stage itself is part of the play, built moment by moment from the collective behavior of countless tiny actors. This isn't just philosophy. It's a seismic shift in cosmology, forcing us to rewrite the rules of everything from black holes to the Big Bang. Take gravity, for example. In general relativity, gravity is the curvature of spacetime, a warp in the fabric caused by mass. But if spacetime is emergent, then gravity isn't bending some pre-existing structure. It's more like a crowd wave in a stadium, the illusion of motion created by thousands of individuals standing and sitting in sync. In this view, the force that holds planets in orbit might not be fundamental at all, but a side effect of deeper quantum processes, like thermodynamics emerging from the chaos of molecules. The holographic principle takes this even further. If spacetime emerges from quantum data encoded on a two-dimensional surface, then the vast, three-dimensional universe we perceive is akin to a mirage, a shimmering projection from some distant cosmic boundary. This would mean that every event, every particle, every ripple of gravity is just the universe, rendering itself into existence, like a video game generating a forest only when you walk into it. Suddenly, phenomena like dark energy, the mysterious force accelerating the universe's expansion, might not be strange anomalies, but clues about the underlying code. But how do we test such a radical idea? One approach looks to the cosmic microwave background, the afterglow of the Big Bang. If spacetime is pixelated at the smallest scales, these imperfections might leave faint fingerprints in the ancient light, like static in an otherwise smooth radio signal. Another avenue is quantum entanglement. Experiments have shown that entangled particles seem to know each other's states instantly, defying classical notions of distance. In an emergent spacetime framework, this spooky connection isn't magic, it's architecture. Entanglement could literally stitch spacetime together, weaving the illusion of separation from threads of quantum correlation. The implications for cosmology are staggering. If spacetime isn't fundamental, then the Big Bang wasn't an explosion in space and time, but the birth of space and time. A phase transition where quantum information first crystallized into the dimensions we know. Black holes, those cosmic drains where spacetime breaks down, might not be endpoints, but windows into the deeper, pre-geometric reality. Even the arrow of time, the relentless march from past to future, could be an emergent property, like the directionality of a river emerging from countless molecular collisions. This new paradigm doesn't just solve old puzzles, it raises profound new questions. If spacetime is built from quantum interactions, what happens when those interactions fail? Could there be cosmic glitches where the fabric frays? And if the universe computes itself into existence, who or what wrote the program? The answers might lie at the intersection of physics and information theory, where reality isn't made of stuff but of bits. For now, emergent spacetime remains a frontier, a wild and untamed landscape where the old maps no longer apply. But one thing is certain, if this vision holds, we're not just observers of the cosmos. We're participants in its construction, living in a reality that's far more dynamic, far more interconnected, and far stranger than we ever dreamed. The Big Bang has long been portrayed as the ultimate cosmic birth, a fiery explosion that birthed space, time, and matter in a single cataclysmic instant. But what if that iconic moment wasn't an explosion at all? What if it was more like a cosmic boot-up sequence, where the universe transitioned from a flat, information-rich surface into the three-dimensional reality we know today? This is the radical possibility the holographic principle brings to cosmology. Instead of a singularity, a point of infinite density where physics breaks down, the Big Bang might have been a phase transition, a moment when quantum data on a two-dimensional boundary rendered itself into the depth and texture of spacetime. Imagine a frozen lake at winter's end. As temperatures rise, the ice doesn't vanish, it transforms, melting into liquid water. The holographic Big Bang could be like that. Not a creation from nothing, but a rearrangement of information from one state to another. In this view, the pre-bang universe wasn't empty. It was a lower dimensional realm humming with quantum activity, like the surface of a black hole's event horizon stretched to cosmic proportions. Then, through mechanisms we're still unraveling, that data unfolded into the three dimensions we inhabit, like a pop-up book suddenly gaining depth. This idea isn't just speculative poetry, it's grounded in the math of string theory and black hole thermodynamics. When physicists model the holographic principle backward in time, they find that the early universe's extreme density and heat could have been the smearing out of information from a 2D boundary into 3D space. The cosmic microwave background, the afterglow of the Big Bang, might even carry faint imprints of this process, like echoes of a dimensional leap. Some researchers suggest that the universe's startling uniformity, the near-identical temperature of radiation across the sky, isn't just luck. It could be a relic of that primordial surface, where every point was quantum entangled with every other before the transition. But here, where it gets even stranger. If the Big Bang was a holographic transformation, it challenges our very idea of a beginning. Time, as we understand it, might have emerged alongside space, meaning there was no before in the classical sense. The question, what caused the Big Bang, could be as nonsensical as asking what's north of the North Pole. Instead, causality itself might be an emergent property, a side effect of the universe's quantum code resolving into a timeline. This perspective also reshapes our understanding of cosmic inflation, the theory that the universe expanded exponentially in its first fractions of a second. In a holographic framework, inflation might not be space stretching, but information decompressing, like a zip file unpacking into the richness of reality. And if that's true, the mysterious dark energy accelerating the universe's expansion today could be a lingering trace of that initial unpacking, a cosmic habit of returning to its flatter, more fundamental state. Of course, this raises existential questions. If our 3D world is a projection, does that mean other renditions of reality could exist? Could there be parallel universes unfolding from the same quantum surface, like alternate tracks on a vinyl record? While these ideas remain speculative, they highlight the holographic principle's power to reframe not just the Big Bang, but the nature of existence itself. The universe might not have started with a bang, but with a transformation, a flickering into depth from the quiet hum of quantum data. And if that's true, then every galaxy, every atom, even the space between these words, is part of a cosmic illusion so vast and intricate, we're only beginning to see the edges of the frame. Dark matter and dark energy have long been the ghosts in the cosmic machine, invisible forces shaping the universe while eluding direct detection. We know dark matter's gravitational pull holds galaxies together like invisible glue, and dark energy drives the accelerating expansion of space itself. Yet, despite decades of searching, their true nature remains one of physics' greatest enigmas. But what if these mysteries aren't flaws in our theories, but clues pointing to a deeper reality? The holographic principle offers a provocative twist. Dark matter and dark energy might not be things at all, but side effects of spacetime's hidden architecture, artifacts of the universe's underlying code. Picture a glitch in a virtual world. When a video game character encounters an unexplained force, say, an invisible barrier or a sudden acceleration, it's not because the programmers added a secret entity. It's because the game's engine, its underlying rules, behave in ways the surface level can't fully account for. Similarly, if spacetime emerges from quantum data on a two-dimensional boundary, dark matter's gravitational effects might stem from how that data is processed. Think of it like cosmic background noise, an imprint of the universe's projection mechanism, not an exotic particle waiting to be discovered. This idea gains traction when you examine the numbers. Simulations of holographic universes suggest that quantum entanglement, the same phenomenon linking particles across vast distances, could generate extra effective gravity in certain regions, mimicking dark matter's pull. Meanwhile, dark energy's relentless push outward might reflect the universe's attempt to maintain equilibrium between its 3D projection and its 2D source, like a stretched spring resisting compression. Some models even propose that what we call dark energy is simply the energy cost of rendering spacetime in real time, a cosmic tax paid by the universe to sustain the illusion of depth. Critics argue this is speculative, and they're right. Traditional dark matter searches focus on WIMPs, weakly interacting massive particles, or axions, hoping to catch these elusive particles in underground detectors or particle colliders. But after years of null results, alternative explanations are gaining attention. The holographic approach doesn't discard dark matter's observed effects, it reinterprets their origin. Instead of invisible matter, galactic rotation curves and gravitational lensing could arise from quantum corrections to gravity at cosmic scales, a subtle rewiring of equations by the universe's holographic wiring. The stakes couldn't be higher. If holography explains dark energy, it might solve the cosmological constant problem, the staggering mismatch between quantum field theory's predictions and the observed acceleration of the universe. In this framework, dark energy isn't a mysterious, repulsive force, but a signature of the boundary's influence, like the way a movie screen's edges subtly distort the image projected onto it. Recent studies of large-scale galaxy distributions show faint anomalies that align with holographic predictions, like shadows of a deeper structure. Of course, this isn't a settled debate. Competing theories, from modified gravity to primordial black holes, offer their own compelling narratives. But the holographic principle's power lies in its economy. It doesn't invent new substances to fill the gaps. It reveals how the gaps themselves might be illusions, artifacts of our limited perspective. Whether this vision holds up to future tests, from next-gen telescopes to quantum gravity experiments, remains to be seen. But one thing is certain. If dark matter and dark energy are holographic echoes, the universe is even stranger and even more elegant than we dared imagine. time moves in one direction, or at least that's how it feels. We remember the past, experience the present, and anticipate the future in what seems like an unbreakable sequence. But what if time's arrow isn't woven into the fabric of reality? What if it's more like a shadow cast by something deeper, a side effect of how the universe processes information? This is the startling implication of the holographic principle. Time itself might be an illusion, an emergent property bubbling up from quantum interactions on some distant, two-dimensional surface. Think of a movie playing on a screen. The story unfolds linearly, characters age, events progress, but the film strip itself is static, every frame existing simultaneously. The illusion of time comes from the projector's light scanning those frames in sequence. In a holographic universe, time could work the same way. The past, present, and future might all coexist out there on the cosmic boundary, with our experience of flow stemming from how quantum data gets translated into the 3D projection we call reality. This isn't just philosophical musing. The equations of quantum gravity suggest that time, like space, might dissolve at the most fundamental level, leaving only relationships between events. A cosmic network where before and after are as fluid as left and right in a hall of mirrors. Black holes offer a clue to this temporal puzzle. Near a black hole's event horizon, time slows to a crawl relative to the outside universe, a phenomenon called gravitational time dilation. From the perspective of someone falling in, time passes normally, but to a distant observer, their descent appears frozen. In a holographic framework, this isn't just distortion. It's evidence that time isn't absolute, but a dynamic feature emerging from how information is encoded and retrieved. The boundary of the black hole, where data gets stored, doesn't experience time as we do. It's more like a hard drive where all states exist at once, with time arising only when the data is played back into the projected universe. This reshapes how we view causality, the idea that causes must precede effects. In a holographic cosmos, entanglement could link events in ways that defy linear time. Experiments in quantum mechanics already hint at this. Delayed choice experiments show that decisions made now can alter the outcome of measurements that already happened, as if the universe is retroactively editing its own script. If time is emergent, then cause and effect might not be the universe's bedrock rules, but patterns that emerge from a timeless quantum substrate, like ripples forming on a pond's surface while the water beneath remains unchanged. So what does this mean for our everyday experience? If time isn't fundamental, then free will and destiny take on new shades. The past might not be fixed, but a configuration of data that's constantly being rendered in tandem with the present. The future could be less a blank page and more a superposition of possibilities, collapsing into reality through observation and interaction. Even aging might be reinterpreted, not as an inevitable march toward entropy, but as a holographic artifact, a reflection of how deeply our perception is woven into the universe's projection. The implications ripple outward. If time is emergent, then the Big Bang wasn't the beginning of time, but the moment time became, a phase transition from a timeless quantum state to a universe with clocks and calendars. It challenges the very language we use. Saying time passes might be as misleading as saying the air is blue. The air isn't inherently blue, it scatters sunlight that way. Similarly, time might not flow at all. We might just be catching glimpses of a deeper, more interconnected reality, one frame at a time. This doesn't make time any less real to us, of course. Our lives, our memories, even the ticking of a clock are undeniably vivid. But it does suggest that time, like space, might be part of the universe's grand illusion, a shimmering surface over depths we're only beginning to fathom. And if that's true, then every second that slips by isn't vanishing. It's just another piece of the hologram waiting to be read. Quantum fields are the invisible scaffolding of reality. vast, omnipresent entities that fill every corner of the universe, vibrating with potential. According to quantum field theory, particles like electrons and quarks aren't tiny balls but fleeting ripples in these fields, like waves on an endless ocean. But what if these fields and the particles they create aren't fundamental at all? What if they're holographic projections, shadows cast by quantum data dancing on a lower dimensional surface? This is where the holographic principle collides with quantum field theory, reshaping our understanding of matter and energy in ways that defy intuition. Picture a concert hall where every note played by an orchestra emerges from the vibrations of a single, massive speaker. The music seems to come from all directions, filling the space with depth and texture, yet its source is flat and finite. In a holographic universe, quantum fields could work the same way. The electrons, photons, and other particles we detect might not be independent entities, but excitations of a deeper, two-dimensional data structure, like pixels on a screen generating the illusion of three-dimensional sound. The equations of string theory and AdSCFT correspondence support this. They show how interactions in a lower dimensional quantum system can perfectly mimic the behavior of higher dimensional fields, as if the universe is running a cosmic simulation where the code is simpler than the output. This perspective flips traditional particle physics on its head. Instead of thinking of particles as the building blocks of reality, we might need to view them as artifacts, side effects of how information is processed at the universe's boundaries. Take the field, for instance. This invisible field gives particles their mass by interacting with them like cosmic molasses. In a holographic framework, the mechanism might not be a property of space itself, but a consequence of how data on the lower dimensional boundary translates into our 3D experience. The molasses could be an emergent effect, like the lag you feel when dragging a cursor across a slow rendering screen. Even more mind-bending is the fate of energy. In classical physics, energy is conserved. It can't be created or destroyed, only transformed. But if energy arises from holographic projections, its conservation might be a secondary law, a shadow of deeper informational symmetries on the boundary. Imagine a video game where the energy of characters is just a variable in the program, subject to the game's rules rather than any physical necessity. Similarly, the universe's energy could be a dynamic output of its underlying code, with phenomena like dark energy reflecting adjustments in how that code is processed. The implications ripple across cosmology. If quantum fields are projections, then the vacuum of space, far from being empty, might be a seething holographic display, its apparent emptiness packed with virtual particles flickering in and out of existence like pixels refreshing on a screen. This could explain anomalies like the effect, where unaccountable forces arise between closely spaced plates in a vacuum. What we call quantum fluctuations might actually be glimmers of the boundary's activity, hints of the universe's true, lower dimensional nature. Experiments are beginning to probe these ideas. Researchers using quantum simulators have created tabletop models where higher dimensional behaviors emerge from lower dimensional setups, mimicking how particles might arise from holographic data. Others are analyzing high-energy particle collisions for anomalies that could betray the pixelated grain of spacetime. While definitive proof remains elusive, each experiment inches us closer to answering a profound question. Are quantum fields the universe's foundation, or just the most convincing layer of its illusion? What makes this vision so radical isn't just the redefinition of matter and energy, it's the democratization of reality itself. In a holographic cosmos, the difference between a star and a stone, between light and darkness, might just be a matter of perspective, different patterns of the same underlying data, rendered in the grand projection we call existence. And if that's true, then the search for the fundamental building blocks of nature isn't a hunt for particles or fields. It's a journey to decode the universe's source code, written in a language we're only beginning to understand. What if the universe isn't just like a computer? What if it is one with cosmic-scale neural networks humming beneath the surface of reality? This isn't science fiction. A growing number of physicists are exploring a provocative idea, that the fabric of spacetime might not just encode information like a hologram, but process it like a vast, self-learning AI. At the heart of this hypothesis is a striking parallel. Just as neural networks in our brains use interconnected nodes to process and store information, the universe could be doing the same on an unimaginable scale, with galaxies, particles, and even the laws of physics emerging from something akin to cosmic computation. Take artificial intelligence as an analogy. When you train a neural network to recognize faces, it doesn't store images like a photo album. Instead, it distributes information across countless weighted connections, creating patterns that only emerge when the system runs. Now imagine scaling that up to universal proportions. What we perceive as gravity, quantum fields, or even time could be the universe's way of running its code, the output of a deeper, self-organizing network we're only beginning to glimpse. This idea isn't just poetic. It's rooted in the math of tensor networks, a framework borrowed from machine learning that eerily mirrors the equations describing spacetime structure. The implications are staggering. If the universe operates like a neural network, it could explain why reality seems so finely tuned for complexity. Just as AI systems evolve to optimize certain functions, like minimizing error or maximizing efficiency, the cosmos might learn its own laws through a kind of cosmic trial and error. This could shed light on why constants like the speed of light or the strength of gravity have the precise values they do. They might not be arbitrary numbers, but stable attractors in the universe's training data, emergent properties of a system that's been running for over 13 billion years. But here, where it gets even wilder. If the universe is a neural network, consciousness might not be a fluke of biology, but a feature of the system. Some theorists, like physicists, suggest that what we call consciousness could be a localized expression of the universe's information processing, like a subroutine in a larger program. In this view, your thoughts aren't just in the universe. They are of it, woven into the same fabric that spins galaxies and bends spacetime. It's a modern twist on an ancient idea, that mind and cosmos are inseparable, two sides of a coin we're only now learning to flip. Of course, this raises thorny questions. Who or what set the universe's initial weights and biases? Is there an ultimate training goal, or is the cosmos simply self-organizing in ways we can't yet fathom? And if reality is computational, could we one day hack its code? For now, these remain open frontiers, but the mere possibility reshapes how we see existence. The stars above, the screen in front of you, even the neurons firing as you read these words, all might be threads in a cosmic neural network, learning, adapting, and unfolding in ways that defy our narrow definitions of life, intelligence, and reality itself. This hypothesis doesn't just bridge physics and AI, it blurs the line between the observer and the observed. In a neural network universe, every measurement, every experiment, every conscious observation might not just study the system. It could participate in it, tweaking the cosmic weights in ways we're only beginning to imagine. And that leaves us with a humbling thought. If the universe is indeed a vast, evolving intelligence, then science isn't just our way of understanding it. It's the universe's way of understanding itself. If the universe truly operates like a hologram, with the three-dimensional world emerging from a two-dimensional boundary, this revelation wouldn't just rewrite physics textbooks. It could ignite a technological revolution unlike anything we've seen. Imagine harnessing the fundamental laws of a holographic cosmos to build machines that bend reality itself. Quantum computers, already pushing the limits of computation, might just be the beginning. In a universe where information is the deepest currency, these devices wouldn't merely calculate. They could manipulate the very fabric of space-time, solving problems that today seem impossible by tapping into the cosmic code beneath our perceived reality. Take energy, for instance. If space-time emerges from quantum entanglement, as holography suggests, then energy might not be bound by classical constraints. Theoretical models hint that advanced civilizations could one day exploit the universe's holographic source code to access zero-point energy, the seething quantum fluctuations in what we call empty space. This isn't sci-fi fantasy. It's a potential extension of the effect, where tiny forces arise between plates in a vacuum due to quantum activity. Scale that up, and you're looking at engines powered not by fuel, but by the universe's underlying data structure. The implications for space travel alone are staggering. Imagine ships that don't carry propellant, but ride the quantum foam itself. Then there's communication. In a holographic universe where particles can be entangled across vast distances, instant information transfer might not require breaking the speed of light. Instead, we could leverage the non-local connections that already stitch spacetime together. Prototypes of quantum networks are already in development, but holography takes this further. If every point in space is fundamentally connected through a lower dimensional boundary, future devices might transmit data not through cables or signals, but by directly manipulating the entangled quantum threads that weave reality. Picture a global internet where latency doesn't exist, where information appears at its destination the moment it's sent, as if the entire system were a single, unified mind. But the most radical breakthroughs could lie in material science. If matter is just a particular configuration of quantum information on the universe's boundary, then in theory, we might one day reprogram it. Think of self-healing metals that rearrange their atomic structure on demand, or buildings that adjust their density to withstand earthquakes by altering how their holographic data is rendered. Researchers are already exploring metamaterials, engineered substances with properties not found in nature, that bend light or sound in bizarre ways. Holography could elevate this to an art form, enabling materials that don't just mimic invisibility cloaks, but literally rewrite their physical properties by accessing the cosmic projection layer. Of course, these possibilities come with profound challenges. If we're living in a hologram, tampering with its code carries risks we can't yet fathom. A misstep in manipulating quantum entanglement could unravel local spacetime, creating unpredictable distortions. And the energy required to hack the universe's projection might dwarf anything our current technology can muster. Yet every paradigm shift in science began as an implausible dream, from electricity to relativity to the silicon chip. The holographic principle doesn't just offer new tools, it redefines what's possible, turning the universe from a fixed stage into a dynamic canvas waiting for its next brushstroke. The true frontier, though, isn't just in gadgets or machines, but in how we perceive our place in the cosmos. If holography unlocks technologies that blur the line between physics and information, between observer and observed, it won't just change what we can do, it will change what we are. We might find ourselves not just users of technology, but co-creators of reality, shaping the hologram as it shapes us. And that's the most thrilling implication of all. The universe's greatest secrets might not lie in distant galaxies, but in the quantum whispers just beneath our fingertips. If reality is a holographic projection, a shimmering illusion woven from quantum data on some distant cosmic boundary, then everything we think we know about ourselves is up for grabs. Free will, the bedrock of human identity, suddenly feels like a paradox. Are our choices truly ours, or are they predetermined outputs of a vast, underlying code? The holographic principle doesn't just challenge physics, it unravels the very notion of autonomy. Imagine standing in front of a vending machine, pressing a button and watching a candy bar drop. You feel like you made it happen. But what if the button press, the falling candy, even your desire for it, were all part of a pre-rendered sequence? In a holographic universe, the you making decisions might be as much a projection as the world you're navigating, a character in a cosmic story where the script and the stage are one and the same. Yet here's the twist. Even if our actions emerge from deeper quantum processes, that doesn't necessarily erase free will. Think of a river flowing downhill. Its path is shaped by gravity, rocks, and terrain, physical laws beyond its control, but the water's movement is still spontaneous, responsive, real. Similarly, if consciousness is the universe's way of experiencing itself, then our choices could be both determined and authentic, like ripples in a stream that are inevitable yet unique. The holographic framework might not negate free will, but redefine it, suggesting that agency isn't about breaking the rules of the system, but playing your part within it. Identity, too, takes on a radical new dimension. If the self is just a temporary knot of information in the cosmic projection, what happens to the idea of a fixed me? Eastern philosophies have long argued that the ego is an illusion, a fleeting arrangement of thoughts and sensations. Neuroscience echoes this, showing that the brain constructs a sense of self from fragmented inputs. Holography pushes this further, implying that even the brain itself is part of the projection. You're not just a passenger in your body, you're the body, the mind, and the stage they're standing on, all emerging from the same quantum source code. This doesn't erase individuality. It dissolves the boundaries between self and world, painting existence as a dynamic interplay of data where observer and observed are inseparable. And then there's the nature of existence itself. If reality is a hologram, then suffering, joy, love, all the raw textures of human experience, are neither trivial nor absolute. They're patterns in the cosmic weave, as transient and profound as shadows dancing on a cave wall. This perspective doesn't diminish life's meaning, it amplifies it. Every moment becomes a collaboration between the universe and its own unfolding, a note in a symphony where the composer and the audience are the same. The holographic principle doesn't answer whether life has purpose. It redefines what purpose could even mean in a universe that's less a machine and more a living, evolving idea. Perhaps the most humbling implication is this: if we're holographic, then the search for truth isn't a journey outward but inward. The mysteries of black holes, quantum entanglement, even consciousness might not be puzzles to solve, but reflections of a deeper unity we're only beginning to sense. In a projected reality, the greatest discoveries won't come from looking further away, but from learning to read the symbols hidden in the fabric of now. The way a single drop of water can reveal the taste of the entire sea. Parallel universes have long danced at the edges of scientific speculation. Alternate timelines where every choice branches into new realities. Unseen dimensions folded beyond our perception. Even entire cosmoses bubbling in an endless multiverse. But what if these myriad worlds aren't just separate universes at all? What if they're all part of the same cosmic hologram, flickering projections of a single, higher dimensional surface? The holographic principle doesn't just reshape our universe. It could redefine the multiverse itself, turning science fiction's wildest dreams into a startling mathematical possibility. Picture a library where every book is written in invisible ink, their pages blank until held under the right light. In a holographic multiverse, alternate realities might work the same way, latent possibilities encoded on a shared boundary, only rendering into full existence when observed or triggered. This isn't just poetic imagery. The same equations that suggest our 3D universe emerges from a 2D surface also hint that multiple, seemingly independent realities could coexist as different reads of the same underlying data. String theory's landscape of possible universes, each with its own physical constants, might not be separate creations but parallel projections, like countless films playing simultaneously on the same reel. The implications ripple through modern cosmology. Take the many worlds interpretation of quantum mechanics, where every quantum decision spawns a new timeline. In a holographic framework, these branching realities wouldn't need infinite space to unfold. They'd simply be different configurations of the same quantum information on the boundary, like alternate cycling on a single monitor. Even the inflationary multiverse, where pocket universes inflate endlessly like bubbles in cosmic foam, could find a holographic twist. Those bubbles might not float in some higher dimensional void, but exist as overlapping projections, their apparent separation an illusion of the cosmic code. But how could we ever test such an idea? Surprisingly, clues might lie in the cosmic microwave background, the afterglow of the Big Bang. If our universe collided with another in the distant past, the holographic boundary could retain scars of that encounter, subtle temperature variations or polarization patterns that betray a brush with another reality. Some physicists even propose that quantum entanglement, which already defies classical notions of distance, could be the thread linking parallel holographic universes. Particles separated by light years might not just be connected, they could be echoes of the same data point rendered in different projections. This vision doesn't just expand the multiverse, it collapses it into something stranger. Alternate realities might not be out there in some unreachable beyond, but nested within the architecture of our own universe, like layers in a cosmic onion. The boundaries between worlds could be as thin as the screen you're reading this on, their separation an artifact of perception rather than physics. And if that's true, the most profound question is whether other universes exist. It's whether they were ever truly separate to begin with, or just facets of a single, shimmering hologram we're all learning to read. The human brain might be the most complex object in the known universe, a 3-pound web of neurons firing in intricate patterns that give rise to consciousness itself. But what if those patterns aren't just processing reality? What if they're actively constructing it, translating a holographic universe into the rich sensory experience we call the world? This startling possibility bridges neuroscience and quantum physics, suggesting that our brains don't passively perceive reality. They participate in rendering it, like a graphics card interpreting code into vivid imagery. Consider how vision works. Your eyes don't see objects directly. They capture fragmented light patterns that your brain stitches into coherent images. Now zoom out. If the universe is a holographic projection, your brain's role escalates from interpreter to co-creator. Neurologists have long known that perception is a constructed illusion. Phantom limbs, optical illusions, and even dreams prove the brain can generate reality without external input. The holographic principle takes this further, proposing that what we experience as solid isn't just filtered through the brain, but actively decoded from a deeper, information-rich layer. It's as if the cosmos streams data and consciousness is the software that renders it into trees, stars, and the screen in front of you. This idea finds eerie support in the brain's structure. Neurons don't store memories in single locations but distribute them across networks, much like holographic film where each fragment contains the whole image. Damage one area and memories persist, a resilience that mirrors how a holographic universe preserves information even when parts are obscured. Neurophysiologists first connected these dots in the 1960s, suggesting the brain might process information holographically. Pair this with physicist David's theory of an implicate order, a hidden dimension where reality is enfolded like an unplayed symphony, and you get a provocative synthesis. The brain unfolds the hologram, translating cosmic data into the familiar textures of life. But here, where it gets even stranger. If consciousness is a decoding mechanism, then subjective experience, the redness of an apple, the warmth of sunlight, might not be locked inside our skulls. It could be a collaborative phenomenon, a dance between the universe's quantum boundary and our neural circuitry. Quantum biologist Stewart and physicist Roger speculate that microtubules, tiny structures within neurons, might harness quantum vibrations to interface with this deeper reality. In their view, consciousness isn't just emergent biology. It's a bridge between the holographic universe's code and the world we perceive. Experiments are probing these radical ideas. Studies using transcranial magnetic stimulation show that altering brain activity can warp perception of time, space, even selfhood, hinting that reality's settings are more adjustable than we thought. Meanwhile, psychedelic research reveals that substances like psilocybin disrupt normal neural hierarchies, often producing reports of ego dissolution and unity with the cosmos. Experiences some scientists liken to glimpsing the holographic substrate beneath everyday perception. The implications ripple beyond science into philosophy. If consciousness and holographic reality are intertwined, then the line between mind and world blurs. Your thoughts aren't just reactions to reality, they might be threads in its fabric, shaping the universe as it shapes you. This isn't solipsism, it's a participatory vision where observer and observed are partners in creation. Ancient mystics spoke of this unity. Modern physics might be catching up. So the next time you pause to admire a sunset, consider this. The colors you see, the emotions they stir, even the sense of you witnessing it all, none of it may be as solid as it feels. Instead, you might be the universe's way of experiencing itself, a flicker of awareness in a grand holographic dance where every thought, every sensation is part of the cosmic code unfolding. Art has always been a mirror to the universe's deepest mysteries. Long before physicists pondered holograms, painters were bending reality on canvas. Consider the Renaissance masters who pioneered perspective, creating the illusion of depth on flat surfaces with nothing but pigment and geometry. Centuries later, Salvador's melting clocks warped time itself into surreal tableaus, while MC's impossible staircases twisted space into mind-bending paradoxes. These weren't just aesthetic experiments. They were intuitive explorations of dimensions beyond the obvious, as if artists were tuning into truths science would later chase with equations. Today, as the holographic principle reshapes our understanding of reality, a new frontier of creativity is emerging, one where art doesn't just depict the world, but interrogates its very fabric. Imagine walking into a gallery where sculptures aren't carved from marble, but woven from entangled light. Contemporary artists like James have already blurred the line between material and illusion, crafting immersive installations that make empty space feel tangible. In a holographic universe, such work takes on prophetic resonance. Slight chambers where viewers lose all sense of depth and boundary echo the physics of event horizons, those cosmic thresholds where information flattens into two-dimensional code. Could future artists use quantum principles to create works that literally change based on the observer's position, playing with the idea that reality itself is a collaborative projection? The parallels between art and holography run deeper than technique. Both thrive on the interplay of pattern and perception. Take pointillism, where thousands of discrete dots coalesce into vivid images when viewed from a distance. It's a striking metaphor for how pixelated quantum data on the universe's boundary might render our three-dimensional world. Or consider Sinfinity rooms, where mirrored walls multiply reflections into endless recursion. A visual echo of the holographic principle's claim that every fragment of space contains the whole. Even digital art's rise feels symbolic. We now routinely experience worlds conjured from binary code, training our minds to accept that reality might itself be an information construct. But the most radical potential lies in collaboration between artists and scientists. Picture a neural network trained on holographic physics, generating visuals that evolve based on real-time data from quantum computers, or a symphony composed using the vibrational frequencies of string theory, translating higher-dimensional mathematics into sound. Some pioneers are already bridging these worlds. Team Lab's digital installations, where flowers bloom and fade in response to viewer movement, hint at a future where art is no longer static, but a dynamic dialogue between observer and projected reality. This convergence raises profound questions about creativity itself. If the universe is a hologram, is artistic inspiration a kind of quantum resonance, a tuning into the cosmic code? The ancient Greeks believed muses whispered ideas to mortals. Modern physics might frame that as entanglement, with artists unconsciously syncing to the universe's informational hum. Whether through brushstrokes or algorithms, art may be humanity's most intuitive probe into the holographic depths, a way of seeing the unseen long before science finds the words to explain it. As technology advances, we might witness entirely new art forms born from holographic principles. Imagine holographic poetry where words rearrange based on the reader's gaze, or virtual reality experiences that simulate navigating a 2D boundary while perceiving 3D emergence. The line between artist and physicist could blur entirely, giving rise to a new renaissance where creativity and cosmology are inseparable. After all, if reality is a projection, then every act of creation is a collaboration with the universe's deepest architecture, a dance between the seen and the hidden, the measured and the imagined. And in that dance, art becomes more than expression. It becomes revelation. The holographic principle has reshaped how we see reality, but for all its elegance, it's not the final answer, just the latest chapter in a story still being written. Even its staunchest advocates admit there are gaps in the theory, puzzles it can't yet solve. For instance, while the math works beautifully for hypothetical universes with negative curvature, our own cosmos appears flat or slightly positively curved. It's like having a master key that fits every lock except the one on your front door. Researchers are racing to adapt the framework to our universe's geometry, but so far, the adjustments feel like patches rather than breakthroughs. And then there's the elephant in the room. If space-time emerges from quantum data on a boundary, where is that boundary? Is it the edge of the observable universe, some unreachable horizon? Or is it a mathematical abstraction, a conceptual surface that doesn't correspond to a physical location? These aren't minor quibbles, they're foundational questions that keep physicists up at night. Critics also point to the principle's shaky empirical footing. Unlike general relativity, which predicted gravitational waves a century before we detected them, or quantum mechanics, which birthed the transistor, holography hasn't yet delivered a testable prediction that can't be explained by conventional theories. This hunt for spacetimes came up empty, and anomalies in the cosmic microwave background could still be cosmic dust rather than holographic fingerprints. Some argue that until the principle makes a bold, falsifiable claim, one that could disprove it if wrong, it risks becoming a beautiful idea trapped in mathematical abstraction. Even one of its pioneers concedes that the theory might be a bridge to something deeper, a temporary scaffold while we search for the true architecture of reality. Yet the most tantalizing unknowns aren't just about the science, they're about the philosophy. If reality is a hologram, what does that imply for causality, for time, for the very notion of objective truth? The principle blurs the line between the physical and the informational in ways that unsettle even seasoned thinkers. Take quantum entanglement. If particles remain mysteriously linked across vast distances, could that be a glitch in the projection, a sign that the universe's rendering engine is struggling to maintain the illusion of separation? And if consciousness plays a role in collapsing quantum states, as some interpretations suggest, does that mean our minds are part of the hologram's operating system? These questions push into territory where physics, metaphysics, and even spirituality collide, leaving us without a clear map. The journey ahead is anything but linear. Competing frameworks like loop quantum gravity and causal dynamical triangulation offer their own compelling visions, each with strengths holography can't match. Some theorists propose that spacetime might be built from discrete loops or geometric atoms, not projected from a distant screen. Others explore emergent gravity models where spacetime bubbles up from quantum entanglement like foam on a deep ocean. The holographic principle isn't racing toward a finish line. It's part of a sprawling, chaotic dialogue where every answer spawns new questions. What's undeniable is how much the principle has already transformed the conversation. Even if future physics outgrows it, holography's legacy will endure like Newton's laws before. It's forced us to rethink the most basic assumptions. That space has volume, that time flows, that reality is there independent of us. Whether it's the final word or just a stepping stone, one thing's certain: the universe is far weirder, far more wondrous than we ever imagined. And the next breakthrough might not come from refining the math, but from asking the question no one has thought to ask yet. Hollywood loves a good hologram, floating displays projecting blueprints for superheroes, glitching simulations hiding dystopian truths, even entire worlds revealed as elaborate digital deceptions. But while these tropes make for thrilling sci-fi, they've left the public with some wildly wrong ideas about what the holographic principle actually means. Let's clear the air. The universe isn't a glitchy simulation run by machines, and you're not from the Matrix. The real science is far stranger and far more fascinating than fiction's flashy illusions. One of the biggest myths, that a holographic universe implies we're living in a computer. While the analogy of cosmic computation can be useful, the holographic principle isn't about silicon chips or alien programmers. It's a mathematical framework suggesting that spacetime's three-dimensional richness emerges from quantum information encoded on a two-dimensional boundary, like how a 3D movie emerges from a flat screen. There's no evidence of deliberate coding or external creators. The universe isn't like a hologram in the sci-fi sense. It is one in a deeply structural way, with gravity and quantum mechanics intertwined in a dance we're still deciphering. Then there's the confusion about projection. Pop culture often depicts holograms as ethereal images hanging in midair, but the cosmic version doesn't require a projector or a screen. The universe's holographic nature isn't about light beams or pixels. It's about how information itself behaves at the most fundamental level. Think of it like a novel where every page contains the entire story, just from a different perspective. The plot isn't being projected onto the pages. The pages are the story, arranged in a way that creates the illusion of depth when read sequentially. Similarly, the universe's 2D boundary doesn't beam reality into existence. It is reality, with our experience of space and time unfolding from its quantum data. Another common mix-up involves solidity. Just because reality might be holographic doesn't mean you can walk through walls or reprogram matter with your mind. Your coffee cup still obeys the laws of physics, and your hand won't phase through it no matter how deeply you meditate on quantum entanglement. The holographic principle operates at scales trillions of times smaller than atoms, governing the fabric of spacetime itself, not the macroscopic world we navigate daily. It's the difference between saying water is made of molecules and claiming you can't get wet because it's just H2O. The universe's underlying structure doesn't negate its tangible consequences. It explains them. Perhaps the most persistent myth is that holography undermines the realness of existence. If everything's a projection, does anything matter? This existential anxiety misses the point. The holographic principle doesn't render life illusory. It reveals that reality is richer and more interconnected than we imagined. Your joy, your struggles, the stars above, they're no less meaningful because they emerge from quantum data. If anything, the idea that the universe literally encodes itself in every part of itself makes existence more wondrous. A hologram isn't a fake, it's a marvel of information and light. And in that sense, the cosmos might be the greatest marvel of all. So the next time someone claims the holographic principle means we're living in a simulation, or that reality is just information, remember, science isn't diminishing the world. It's showing us how much more there is to discover. The truth isn't colder than the myths, it's brighter, weirder, and infinitely more compelling. And that's no illusion, the race to prove or disprove. The holographic principle is heating up, with scientists designing experiments so precise they border on science fiction. At the forefront are next-generation interferometers, machines that make today's most sensitive instruments look crude by comparison. Imagine lasers so stable they could detect a vibration smaller than a proton, or mirrors suspended in vacuum chambers so isolated they sense spacetime's quantum fuzz like fingertips brushing over braille. Projects like the successor, dubbed the Cosmic Observer, aim to hunt for holographic noise at scales 1,000 times finer than before. If spacetime is pixelated, these devices could catch it in the act, like capturing the individual frames of a movie projected at light speed. But interferometers are just one piece of the puzzle. Deep underground, in abandoned mines and mountain tunnels, another revolution is brewing: quantum gravity probes. These aren't telescopes pointed at the stars, but sensors tuned to the whispers of the Earth itself. By monitoring the subtle vibrations of crystalline materials cooled to near absolute zero, physicists hope to detect anomalies that betray spacetime's granular structure. Think of it like listening to a symphony through a wall. The melodies might be muffled, but the rhythm of the universe's underlying code could still shine through. Early prototypes have already spotted tantalizing deviations from classical physics, hints that gravity might indeed emerge from quantum entanglement, just as holography predicts. Then there's the cosmic frontier. The James Space Telescope's stunning images are just the beginning. Proposed missions like the Cosmic Holography Explorer would scan the microwave background for patterns that resemble error-correcting codes, a telltale sign of holographic encoding. Other teams are analyzing gamma-ray bursts, the most energetic event since the Big Bang, for subtle distortions that could reveal spacetime's pixelated nature. It's like examining the brushstrokes on a masterpiece to deduce the artist's technique, except the canvas is the entire observable universe. Perhaps the most audacious experiments are happening in quantum simulators, where researchers recreate black hole conditions using ultra-cold atoms trapped in laser grids. These lab-made universes allow scientists to manipulate quantum entanglement like dials on a control panel, watching how simulated spacetime bends, twists, or even fractures under extreme conditions. Recent breakthroughs at institutions like and the Perimeter Institute have shown that entanglement entropy, a measure of quantum connectedness, directly influences the geometry of these artificial spacetimes, just as holographic math suggests. It's not proof yet, but it's a clue that the universe's deepest secrets might be hiding in plain sight, written in the language of quantum links. What makes this era so electrifying isn't just the technology, it's the stakes. If even one of these experiments confirms holographic predictions, it wouldn't just validate a theory. It would rewrite the rules of reality, proving that space, time, and gravity aren't fundamental but shimmering mirages over a deeper quantum sea. And if they do, that's equally thrilling. Null results would force physicists back to the drawing board, potentially uncovering even stranger truths. Either way, the next decade promises something extraordinary. Not just answers, but new ways to ask questions we haven't even imagined yet. The universe's greatest trick might be hiding in plain sight, waiting for the right experiment to pull back the curtain. As we've explored, the idea that reality might be a hologram is more than a wild speculation. It's a serious scientific hypothesis with profound implications. From black holes to quantum entanglement, the evidence challenges our deepest assumptions about existence. Whether the holographic principle holds or not, it pushes the boundaries of human knowledge, inviting us to question, explore, and marvel at the universe's mysteries. If reality is a hologram, what else might we discover when we look closer? The adventure is just beginning. Think about the first time you held a holographic card, tilting it to watch the image shift and transform. That simple trick of light and perspective felt magical, yet it was just a glimpse of how much more there could be. Now imagine that same principle scaled up to cosmic proportions, where the stars above, the ground beneath your feet, even the thoughts in your mind are part of an illusion so vast and intricate, we're only starting to trace its edges. This isn't about dismissing reality as a mirage. It's about uncovering the hidden machinery that makes the mirage feel so real. The holographic principle forces us to confront a humbling truth. Our senses and instruments might only reveal a fraction of what's truly there. For centuries, we've treated space and time as the unchanging stage of the cosmos. But if they're emergent phenomena, like the warmth that arises from a crowd's collective breath, then the universe is far stranger than we ever imagined. It's as if we've been studying the surface of an ocean, mistaking the waves for the water itself, while the currents below remain unseen. What's thrilling is how much room this leaves for discovery. Every unanswered question, dark matter's grip on galaxies, the enigma of consciousness, even the nature of time, could be a doorway into that deeper layer. The holographic principle doesn't just solve puzzles, it reframes them, turning gaps in our knowledge into invitations to look beyond the obvious. And if history is any guide, the most revolutionary breakthroughs often come from questioning the very things we thought we understood. So where does this leave us? Not at an ending, but at a threshold. Whether the universe is a hologram or something even more astonishing, the journey to find out is what makes science so exhilarating. It's not just about the answers we'll uncover, but the new questions we'll learn to ask. After all, the greatest discoveries begin with a simple realization. There's always more to the story than meets the eye. And in a cosmos this mysterious, that's the most exciting truth.